Hello and welcome, everybody, to another episode of Last Week in Quantum. I'm your host, Bill Roth, self-proclaimed Silicon Valley marketing genius. This is the show where we review the week's news in the world of quantum computing, its impact on the world of cybersecurity, AI, and more. And with us this week to discuss is Brandon Dennis, Director of Operations for QuSecure, and first-time guest, Skip Sanzeri, co-founder and COO of QuSecure. Welcome to you both.
Thank you.
Thank you, Bill.
So last week, Harvard had a breakthrough which brings the quantum computing years closer. Physicists entangle individual molecules for the first time, and DoD offices see post-quantum cryptography as mission critical. Let's get started by talking to our experts. Brandon, article about DARPA and Harvard, tell us about it.
Yeah, let's start off with breakingdefense.com. The article title was Off to the Races. DARPA Harvard breakthrough brings quantum computing years closer. The summary of the article says widespread quantum computing may come years sooner than expected, thanks to a Pentagon-funded project with implications for everything from rapid vaccine development and weather forecasting to cyber warfare and code breaking. Skip, I know you had a chance to read this one. Can you tell us about the 48 perfect qubits?
Yeah, this was pretty amazing, folks. So we've been looking at quantum computing for a while and watching the big companies, IBM, Google, Amazon, Microsoft, Alibaba, and then some of the smaller ones, including IonQ, Rigetti, and others, PsiQuantum out of Palo Alto. And while they've all taken their various qubit routes, very few have taken the atomic qubit, which is like using a neutral atom. In this case, Atom Computing out of Colorado did that. But what was really interesting is these guys had coherent qubits, fully error-corrected qubits, out of the chute. And this was a breakthrough to come up with 48 perfect qubits that need no error correction is amazing. For instance, a lot of the times when we see qubit counts, like we see IBM at 1100 or, Rigetti at 800 or IonQ at 1000, a lot of times those are not error corrected. And in many cases, you need an extra 1,000 qubits for the error correction. So what you get is, you can run fast processes, but it could be 50% wrong. That doesn't help anybody. But when you have a perfect qubit and you're able to run processes with this set of perfect qubits, then you have a lot of reliability on calculations. So the breakthrough was that they used Rydberg atoms, and these are neutral atoms that were exactly the same, which means that you can replicate these and entangle these, and you can use these and interchange them in ways that allowed this breakthrough to be just amazing. And by the way, it came out of nowhere. No one saw this coming. But now what this means is you have power of 2 to the 48th. And if you do that number, that gets to be a pretty big number. If you can scale this at all, let's say just 10 times, where you've got, in this case, 480 perfect qubits, you could do some amazing things on the planet because you would have 2 to the 480th power of calculation. To give you guys just an example, 2 to the 300th, let's say there was a 300 qubit computer, perfect, that calculates more instances than there are atoms in the entire universe. That's 300 qubits. So we're on the way, and this breakthrough really shook up the industry.
Excellent. Thanks for the visibility into that amazing story. Hey, folks, remember to subscribe to our YouTube channel to stay up to date to all things quantum. If you're watching on YouTube or LinkedIn, make sure you subscribe, hit the subscribe button below so that you can be up to speed on everything that happens in the quantum area. So next up, let's talk about entangling. We were just talking about atoms. Let's talk about entangling molecules. Brandon, there was a great story that came out last week on this.
We're going to move over to phys.org, and they mention that physicists entangle individual molecules for the first time, hastening possibilities for quantum computing. So for the first time, a team of Princeton physicists have been able to link together individual molecules into special states that are quantum mechanically entangled. And in these bizarre states, the molecules remain correlated with each other and can interact simultaneously, even if they're miles apart, or indeed, even if they occupy opposite ends of the universe. Skip, can you explain in simple terms how entangling individual molecules works?
Sure. Yeah, it's entanglement's a great property. By the way, this was the one Einstein hated. He did not believe in entanglement. But the way entanglement works is you take a couple subatomic particles, or a couple, in this case, molecules. Hint, hint. We'll talk about that in a minute. But you use something like an example. You can use microwave radiation to create a relationship between the two particles. And what that means now is those particles actually think they're one. And it's a phenomenon no one can explain why it happens. We just know that it does happen, and we can measure that entanglement. So if you separate those entangled items, and Brandon, you said, by a universe, correct, or further, if you reverse spin on one particle, the other one instantly reverses spin, which means that across the universe, it goes faster than the speed of light. It cuts through space-time. And entanglement's an amazing property. Now, the breakthrough you're talking about at Princeton was that they entangled two molecules for the first time. And I want to emphasize here, by the way, these two articles, the one we talked about, before, and this one, all happened within a couple weeks. These breakthroughs are crazy. But on the molecular side, no one had entangled molecules. Remember, the history is first we started with subatomic particles like electrons and the superconducting ones. That's what Google was working on, IBM has, etc. Then we moved into some clever particles like ions and photons. So ion Q, quantum uses photons, got it. Each one has their. Then we moved into neutral atoms, like the article we talked about, or what atom computing is doing out in Colorado. They use neutral atoms, which is not even subatomic because it's atomic, right? But now, to use molecules is crazy because molecules, which are made up of atoms, now give you all sorts of new capability that if this can scale, now again, that's if, and it does take work, you're going to have access to things you never had access to before, ways of calculating, ways of programming that you didn't have access, because now it's not even a quantum computer, it's more of a molecular computer, if you follow me. So it's wild, and now they only entangled two molecules, so not that many yet. But the fact that they did it means that they can do it again, and so we're very, very excited to see where this goes.
Excellent. Our final story of the day comes to us from NextGov. Brandon, tell us about what the DoD is thinking about post-quantum cryptography these days.
Yeah, it's pretty incredible. DoD offices see post-quantum cryptography as mission critical. The article says that officials at the Department of Defense shed light on their agency's plans to modernize their encryption infrastructure ahead of the anticipated advent of a fault-tolerant quantum computer, discussing familiar policy goals like private sector collaboration and supporting warfighter operations moving into 2024. We know post-quantum is imperative for the security of our nation. And Skip, I'd love to hear your take.
Yeah, I mean, we were just talking about major breakthroughs, folks, in the last 2 weeks, right? Not even in the past months or years. This is what's happening here. And Hartmut Neven said this best from Google. He said that the quantum speedups will be double exponential. So, in other words, they're going to speed up at rates that we won't be able to track. And that means that this idea of a cryptographically relevant quantum computer, or a quantum computer that can break our cryptography, is coming at us much faster. You think about the breakthrough with the 48 perfect qubits. Well, again, they start scaling that. This is going to be here on us really quickly. And I think the DoD and federal government know that the upgrade is going to take a long time. It's not going to happen overnight. It's going to take years to upgrade. So in essence, we're behind the curve already. But what's important here is to think about, especially when they're thinking about this type of cryptography, is think about being crypto agile and being backwards compatible, being able to install new cryptography to start battling these things, but also not removing your existing crypto. That is the way it has to happen, and it'll happen fastest that way, but we don't have to switch things out. But DoD, Office of Management and Budget, certainly three-letter agencies here in the U.S., they all know that there are billions being invested around the planet to get this quantum computer online that can crack cryptography first. And that's going to be a problem if the cryptography isn't in place. The post-quantum cryptography isn't there prior to that happening. So we are behind the curve. The federal government knows it now. They know that we need to speed up. The pressure's on because, remember, it was December 2022 when Biden signed into law H.R. 7535, which is the Quantum Security Preparedness Act. They signed that a year ago. Now they're saying, okay, we're behind. Let's pick up the pace. Let's get this stuff in place. And the last thing I would say is the cryptography that's protecting communications on the internet, it's 50 years old. It was invented in the late 70s. Now we've increased key sizes to stay ahead of our regular computers, but at this point it's time to move to new cryptography that's agile and backwards compatible, and this way we're protected and future-proof.
Excellent. Thanks very much. And thank you both for all those great stories. Folks, you can find all the links to the articles mentioned today in the show notes. And if you want weekly quantum updates, join our mailing list by visiting our LinkedIn page. That's all for today's show. I'm your host, Bill Roth, humble, self-proclaimed Silicon Valley marketing genius. And with us this week has been Brandon Dennis, Director of Operations, and Skip Sanzeri, co-founder and COO of QuSecure. Thanks for showing up, guys.
Thank you.
Always a pleasure, gentlemen.
We'll see you next week on Last Week in Quantum.